Good afternoon. Thank you for coming. This is one of last talks of this conference. Do you enjoy it so far? Yeah, I enjoyed it very much. Even though I knew what kind of conferences build stuff, I was still a bit surprised when I came here and everything is just literally on the beach. And I have probably the most boring title not title of the talk, but personal title and agenda. I think I'm specified as senior consultant, which actually doesn't really go with the mood of this conference. So I'm glad that the title of the talk didn't fool you. And I won't be telling you about some fluff. We will try also in the good tradition of this conference to talk about some stuff. How to integrate RabbitMQ into actor systems. My name is Vagif, and I'm originally from Russia, but I've been living and working in Norway for about 2 decades. You can find me on Twitter, on some other channels, and all code which I'm going to show today is on GitHub, on my account. I will give you a link. First, let us first go through agenda. So we'll start with a bit of motivation. Why message queues? Why actor model? And then we will delve into showing some code. How are we doing it? The code is mostly from the real project, where we're writing actually a large enterprise system and integrating with queued messages. And system has high availability and performance demand. So we care about such things very much. And this makes it also interesting why have we chosen actor model for that. And then we will start going into some queued message patterns and how we implement them using F#. Let me ask you, who is doing these days WS transactions? Nobody. Is it an indication of something? Because about 10 years ago, a bit less, we all could read about the rosy future days where all transactions we were successfully running on local database. We could be running across the internet, across the web, even though the internet is impossible to manage. Luckily, we were learning, and I was actually very glad hearing the answer Sanders gave to somebody. He was questioned in a bit provocative way if he admits that the previous generation applying OOP to communication at large really fucked up. And he said, probably. So he gave the honest answer. So it's not how these days complex and robust responsive systems being written. So decisions, should it be SOAP versus REST? And I think we're seeing a clear winner now. Then we have learned that in many scenarios we'll be better off running compensating transactions instead of just trying to arrange everything as discrete transaction. Also, message queuing comes as a replacement for synchronous calls. And if you attended Ian Cooper's talk earlier today, he was also talking about that, the decouple things, use message queues. And he was even illustrating it with throwing balls to some volunteers. And of course, reactive versus proactive systems. So the actor model and the use of message queue, it falls very much in the concept of creating reactive systems, which should be responsive, resilient, elastic, and message-driven. I guess we all understand what responsive means. It means that system should at any time give a response to request. It should not be waiting for certain operation to complete before it can accept other requests. Resilient, it's self-queued systems. And this is achieved very much using actor model, where you have pieces of code that create instances of other pieces of code and supervise them and make decisions about what to do if this child code fails. Then it's elasticity, that, which also achieved with using frameworks like Akka, where you can build location transparent system. You can easily scale it and elastically expand it to use remote actors or even actors in clustered scenario. And of course, finally, it's all message driven. So all your pieces of code communicate using messages. If you probably read the books, numerous articles about solid principles, and the first letter S, it's a single responsibility principle. But the principle itself doesn't really show you, tell you much about how you build your code that should be responsible only for a single task. But when it comes to actors, they come with much more strict requirements. First of all, they're also responsible only for a single type of task. But moreover, they run this task in isolation. They don't share anything of their state with the rest of the system. And the only way to communicate with actor is to send them messages. And maybe they will send a message back saying something about their state. That's the only way to get their state. Another thing is that actor must process only one message at a time, which another very strict requirement, which makes it actually much easier to implement such actors, because you're only dealing with a single thread, and which makes functional languages perfect to implement actor-based system. So what can an actor do? As I said, an actor can send messages to other actors. An actor can create other actors. It can supervise actors that it has previously created and stop them even if a fatal situation occurs. And it can change its own state, but the only way to ask its state is to send him a message and ask to send message back about the state. So with that, we can start building systems composed of actors, which will look something like this, where you have these hexagons representing actors, and you will see the actor hierarchy from left to right. So this is a top level actor, and it created two blue actors. One blue actor created a yellow one, which in turn created two purple ones, and they can send messages to each other. These black arrows, it's not creation, it's messages. And messages they can send to children, not children, to any actor itself. But of course, the question that how such systems should communicate with the rest of the world. It would be naive to expect that even in single organization, everything is built using one actor model framework. And it appears that message queuing is actually a very natural answer to that, since actors respond to messages. So the way to give them some work is to send them some messages that they can collect from message queues. But then we have a kind of dilemma, because if something happens on the way to task solution, then we need to be able to tell the message queue the state of this message. In most message queues, you can acknowledge messages by sending either ACK or NACK message, like acknowledge, not acknowledge. So message queue can get back the message and decide what to do next. A message can be requeued, it can be put to some error queue, and message queues are actually very powerful in those functions. So you can configure your message queue saying that time to leave for every individual message is that much, and then after that it goes to error queue, and then you can process message differently. So then it becomes quite important to integrate this message, acknowledge information in your domain messages, which creates some challenge because we don't want to mix domain and infrastructure concerns. Because if something happens here and we want to return message back, then some of these actors can say NAC to the message queue. But then he needs the address of a queue, he needs the ID of the message. And if everything goes fine, then the last actor says ACK. The message is acknowledged and it's removed from the queue forever. So we need to be able to solve this in a nice way. So our code is readable and we don't pollute our domain code with some infrastructure code. So in our project we're using a RabbitMQ. It's one of standards de facto, and not even de facto because it supports some well-recognized standards like MQP, and it runs on any major platform. There are RabbitMQ drivers written for every major language. So it's very easy to get going with RabbitMQ. It has excellent documentation. It's free, open source, etc., etc., etc. So that was our choice. And our choice of platform for actor model on .NET was akka.net. It was also sort of obvious choice for us, but mainly because it's probably the best actor model framework at the time. Microsoft has its own implementation, Orleans, but we like the fact that akka.net, it's also open source. It's very easy to get in touch with developers. It follows original Akka Scala development path, so we know approximately what's going to happen next, and new functions coming rapidly. Just a few days, I think it's 3 days ago, they released cluster support for akka.net, which was in beta for some time. So for the rest of the session, we're going to through some code just to show how we define our messages, how we implement server, client, actor, how we implement queue, reading, and if we have time, maybe I'll have a short demo because I'm running RabbitMQ server on this Mac, so we can use F# Interactive just to send some messages to some queues and see what happens. We'll be using main message patterns, which of course message, which is, I guess, that doesn't require further explanation. Then some messages expect reply, and reply comes on a different channel because it's another message that comes from recipient to sender. And if you look at enterprise integration pattern book, then they also define it as return address pattern. Because sometimes we need that the message after processing trigger some receipt that is sent not to original sender, in addition to of course, to reply that goes to original sender, but it goes to some other actor or queue or something. And this is called return address. And this is actually a perfect fit for our situation where we want acknowledgement messages to be sent to, not to sender of the message, but to some other actor managing our RabbitMQ messages. We really don't want to send acknowledgement back all the way. We want to send it directly. So we're using a return address pattern. So this is F#, and it's quite readable, even for non-technical people, and this is the primitive domain message. Of course, it's not real domain message. It doesn't define anything for any domain, but for demo purposes, it's sufficient. We have request of some string and which generate reply of some string. Then our first approach to implement server actor can look like this. So this is F#, and to implement actor that processes akka.net messages, you need a function, because everything in F# is functions. So this function receives a mailbox. So and then it needs to retrieve messages from this mailbox in the loop. So this is a recursive function that just calls itself all the time. So it receives a message, and then it matches with, using pattern matching with request, and then it sends a reply. And this funny operator is operator tell in actor.net. It's method tell in actor.net, but in F# they overloaded this operator. It says send this message to this actor, which is a sender of the original message. So if we don't think about separation of concerns, then we could have defined our domain message or redefine it like this. We can get some requests, but sometimes we need to have a return address. So we have an alternative message, request with ACK of some actor, everything, all communication entities are actors, and some acknowledgement ID. And we can send replies. But that would be really bad, because then I guess in our system we will have maybe hundreds of domain messages, and if each of them has this overload, sort of overload, it's an additional case of discriminated union, then it will be just a mess of domain-specific information with some infrastructure stuff. So instead, we have chosen to put our messages in envelopes. So we still keep our domain messages clean of any infrastructure concerns. We define an acknowledgement ID as a different type. In RabbitMQ it's unsigned 64. And then we send all messages as envelope of either just message, domain message, that doesn't require any acknowledgement back, or message with ACK, message that requires acknowledgement, which comes as anything with additional acknowledgement information, which is it serves as return address in that pattern that we have seen. To separate concerns even further, we put acknowledgement messages as in a separate type and define special actor that will just deal with acknowledgement. And it corresponds also with recommendation you can read in Bob Vernon's book about implementing domain-driven design using Scala. He suggests that it can give you cleaner implementation if the actual domain servers will not be sending messages to queues directly. Instead, they'll be using some worker actor that will do the work for them. So you see, it's quite simple. It can ACK and it can NACK messages that come into it. And if you look at our revised server implementation, you will see that it's changed. When we create server, or when we enter this function, we create the worker which will acknowledge our queues. So we've received a regular message without acknowledgement requirement. We just reply to sender directly. If we receive message with acknowledgement requirement, we of course reply to sender. And in addition, we send this acknowledgement to our acknowledger. And you see we're using another method here, forward. Forward is a special case in actor model when you want to send a message on behalf of other actor. So what happens here, when the queue, this queue actor receives the acknowledgement, it will believe the acknowledgement came from the server actor and not from this acknowledger. So acknowledgement just as a worker which delivers, just it's a transport, but the actual return address for that message is the server that sent it, which fits perfectly our scenario with sending acknowledgement to RabbitMQ. So then sending messages to server is as easy as writing these lines. If you don't want acknowledgement, you just send message request of something. If you want acknowledgement, you specify also a return address, which is a combination of queue and message type. If you look at how implementation of client actor may look. Client is, in this scenario, it's a piece of code that prepares some data, wrap them in a message, and sends to the server. But for our demo purposes, we won't create new message types. So client will just create the same type of message that server will respond to. The same type of message client will also respond to. So we just tell client, send something to the server, and we already generated that message. And it's simply forwarded to the server with or without acknowledgement requirement. And client can also receive replies. So this is a reply situation. So now, what we need to resolve now, how we load client with work. So our client needs to fetch messages from the queue, from RabbitMQ. Of course, the bad implementation would be to insert directly queue infrastructure code in our client, which otherwise work with domain-specific details. That would break this single responsibility principle, and after suddenly dealing with multiple things. So instead we extract all RabbitMQ specific details and implement new type of messages. It's subscriber message. Which we can use to subscribe to queues and to receive queue messages with or without acknowledgement. Here you can see that we have a case start with, which just follows convention suggested by von Vernon, who in his book used start with and reference to the not necessarily queue, but some message source, to stop following, to stop subscribing to that messages. So with that we can write queue reader actor that will communicate with the queue and send messages that it will extract from the queue to our client. Client will be message handler. So when we create this function, when we invoke this function, it receives some serializer. We need to serialize, deserialize queue messages. We need some function to deal with that. In our case, it can be JSON.NET serializer. But I know that in many Akka developers, they use so-called wire serializer, which is faster. But for our purpose, JSON.NET is fine. And message handler. And this is actually our client that then later will talk to server. So QReader implementation is quite simple. And you can see that we actually implement a state machine. In the beginning, QReader actor is an idle state. If it receives the message start with queue, then it will start listening the queue. And you will see that it enters listening state. So it enters it here. I'm entering different state. And when it's listening state, it keeps getting messages. But all state information it received with a function. So it received its state, and now it starts receiving messages. And what messages can it get? It can get instructions to start with different queue, then it's still in listening state. It can get instruction to stop, then it becomes idle. Or, what is interesting, it can actually get queue messages. In this case, it will serialize or deserialize them and call our message handler. And will stay in listening queue, in listening state. So we haven't shown the actual infrastructure code of that will deal with RabbitMQ API, but so far we can have some observations with the code that we have written. First of all, we managed to keep our domain definitions free of infrastructure concerns. So we have plenty of domain messages. In this demo only one, but in our system it's plenty. And they all only focus on domain specific details. And we have infrastructure messages, something like message envelope, for example. Then, advantage of using F# is that we can easily implement state machines that deal with situation that occurs to particular actor. And as you might notice that we don't have a single mutable variable, which for us was one of the main reasons we have chosen F# and not C# when starting our project. We all were tired of fighting with mutability for many years, of sharing state, of synchronizing state, resolving thread-specific issues. So we wanted to give a try to pure, F# simply not pure, but pure enough functional language that would let us build a system without defining mutable variables. And so far we succeed. And if you attended one of the first talks by Sander, one of the first things he said that when implementing the microservices, they have a trend now. They do it in a functional way, and I have full understanding for that. So now we're approaching RabbitMQ. So how we approach our infrastructure. RabbitMQ deals with exchanges, because Q is a physical message destination, but when we send messages, we send them to some exchange. So it's kind of virtual queue which can be distributed to some physical queues. So when we create or declare our queues, we specify what kind of queue we create. And then you can have direct communication just with one specific queue. You can have fan-out exchange, it's typical pub-sub. And you can have also topic exchange where sender of information can route message with certain types, like error or warning messages. And subscribers can even subscribe on messages using multiple criteria. So actually these are two scenarios, routing and topic exchange. So these are first definitions to approach this goal. Then we need to define types to deal with queue message content. Even though for this purpose of demo we just working with strings, but we define a separate type for that, payload. Then we have type for routing key, because routing key don't necessarily be a strings. And then we have message content, which can be either just content or content with routing key. And then we have finally queue actor commands, which is in fact 5 pairs. So you have 2 commands for connecting, disconnecting, 2 commands for subscribing and unsubscribing to certain queue, then commands to route or unroute messages, then commands to publish and receive messages, and finally ACK and NACK. This is something that queue acknowledge worker will send. So those are 10 commands that our queue actor will use. And since we're working with actor model, it's very important that actors are supervised. So our queue actors will be created by queue factory, which will supervise them and listen to their exceptional situations and make decision what to do with them if exception occurs. So this piece of code, which structurally equal to what we have in our production system, I just removed some details that really not necessary for this demo. So we have a queue actor which has 3 main states: disconnected, connected, and subscribe. So when it's disconnected, it's an idle state. And then the only command it can react to is connect. And then on the connection, here comes Rabbit stuff. So we create connection, we create model, and we start declaring queue, and so on and so on. And then we enter a different state, which is connected state. In connected state, we can do some more interesting things. For example, the client can subscribe to certain queues. Because to send messages to to queue, you don't need to subscribe. But if you want to receive messages, you need to subscribe to that. And the client can do that. It can, of course, disconnect in that state, publish messages, ACK and NACK things. So it's much more powerful state. Finally, there is subscribe state, which, you see, it drags much more data. So the whole active state comes as a parameters of this state function. So in subscribe state, we can, of course, unsubscribe, disconnect, but the most interesting, we can actually, let me go to, the most probably interesting, we can receive messages. And after receiving message, we send it to subscriber with queue message with ACK. So we send the actual content and the title. So this is more or less what happens to between our actors that run in our system, which is, by the way, a system that uploads to the cloud media files. It's media organization, and requests to upload the files, they come through RabbitMQ messages. And of course, since we mentioned Q Factory, I should also give you the code of that. And actually, I think this is exactly how this code looked without any omission. So it's quite simple code, and it has only one message: create exchange, which it racks to. So putting it all together, we have written the code that consists of domain messages that don't have any infrastructure concerns, even though they're highly primitive. Then we have some types to wrap them and add some routing information to return receipts to the originating queues. We have written some code to deal with RabbitMQ and send messages to actors. And we have written very simple, probably too simple, examples of client and server that just send messages, client sends messages to the server and receives reply back. And to fully exploit RabbitMQ integration, we should probably test how it works in different scenarios. And when it comes to Rabbit, you have, as I mentioned earlier, 4 main scenarios. There is also RPC, but that's not the one which was interesting for us. It's work queues where you just directly send message to some queue, and the message will be fetched by the queue reader. You have also publish subscribe when there is a fan out exchange. We send message to some exchange, and we just configure it to redistribute messages to potentially many queues. And every queue has its own reader. It's an actor that takes a message and handle it further. Then we have routing, so we can send messages with routes like arrow, info, like in this example. And then we have the most complicated scenario, topic exchange, where you can not only route Okay, I think I lost. I can just continue with this one. Yeah. So, sorry for that. I didn't do it on purpose. So we have topic exchange where we can send a route message, and clients can actually set some multiple criteria when receiving them. So before I will show you some code. So if you're interested in more code, and you want to read about some inspirational work for us, you can
of course, read more or less everything which was presented here in my blog post. Then the patterns, message exchange patterns that we used, they were taken from the book by Gregor Hoppe and Bobby Wolf, Enterprise Integration Patterns. Then there is a great book by Bob Vernon, in particular on Akka and Scala. And there is a quite inspirational blog post by Jorge Fiorinelli about implementing reactive message patterns using F#, which actually inspired us also to do some of this work. And of course you can get akka.net. And all code is available on my GitHub account. So with that, I guess I will switch off my. Let's see. It's a bit more difficult to show it using just a mic, but.
Ready? Ready. Okay. Thank you. Yes. Now it will be easier. Yeah. So this is a RabbitMQ server that is running on my MacBook. You can get it and install. The easiest to install it on Mac is to use brew command. Then you will get a server which you can start from command line. And this is Xamarin Studio. The code that we write, we deploy on Windows servers, but it runs without problems on Xamarin, actually on this Mac. The only problem I have to solve is just to make sure that I don't use backslash, I just use forward slashes in paths. So all code is here in this solution. You have the server and client and the actual queue actors. So if we now look at F# interactive, I have some simple script which demonstrates how you can send and receive messages using F# interactive console, which is actually one of the way we do some initial tests, because it should never replace your regular tests and tests that you run on every build, but it's very convenient to work with REPL, to work in interactive mode. So what we'll do now, so as you can see, I have queues, direct logs and topic logs, and now there should be a new queue which is called hello. It should appear. So first I load some, I should first clear or restart F# interactive if I want to show you new session. So what I'm doing now, I just send this to F# interactive. Then I create my actor system. And this is, okay, I'll do it one by one. So I created, oops. Let me see. Yeah, now it worked. Then I create my server. And then I create a queue factory. So then I create a client. Another client, just in case. Queue reader and another queue reader. So they will read queue messages and send to clients. And then I declare using queue factory. I send a message, declare exchange, and it will declare exchange with the name hello. And then I think after I connect to the queue, so I'm sending now message connect to my queue. So probably after some time it should, yeah, I see it now. There is a queue called hello. So what I can do now, I can subscribe my queue reader to that queue. Then I'm publishing my content, and you see that client sending request, server receiving request, and client received a reply, which is also high. And if you see the state of the hello queue now, it doesn't have any messages, because when server receives this request, it acts message, and it disappears from the queue. So that's a simple scenario of queue communication using actors. Just to show you something different, we can also try with some PubSub, which not really much different than that. It's just, we just have multiple subscribers. So you see that there are not just one, but a couple of recipients. We can, yeah, publish, disconnect. And you see, well, now there is still one message which is unlocked. Ah, yeah, because I disconnected my clients and then I published another message. So this message is not received yet. So that's not, yeah, that's how it should be. So, so you have seen the code that very close to the production code that we have, that shows how to use actor system, how to integrate it with RabbitMQ, and how to solve with this integrated solution transactional requirements, not classical asset transactional requirements, but process transactional requirements in a sort of eventual consistency sets. That we send some requests using queue, and then request goes through chain of actors, and once request is fulfilled, is processed, the last actor acts it back to the queue. Otherwise, when we receive some exceptions, we get nagged to the queue, and we can decide what to do with the queue further. So, with that, I think we were a little bit over time at the beginning, and we are, I think, a bit over time, but almost. I think we shortened a little. So this is what I was about to tell you about our project and about our use of F#, RabbitMQ, and actor model. So, if you have any questions, I'll try to answer. Questions?
Anyone?
Yeah, here.
Could you please show the slide where you made a transition from discriminated union with two unions where request reply with 3 unions, and the next slide had envelope, message with envelope and so on, because I have a bad suspicions.
Okay, just a second. So that was probably
one of the first slides with the code.
Slideshow.
And the next one.
And that was, I think that was the first.
Second version, I don't know. Second version was here.
This one?
Yes. Okay, but I'm mistaken, but I don't see any message type. I see only the main message type.
It's a message envelope of A, which
oh, sorry.
A is generic type.
Oh yes, exactly. And I was told that I wanted to tell that with this transition from request, reply, and request with egg to message envelope, you, from my viewpoint, I can be mistaken, but you've introduced some kind of rigidity, because when you had three unions, you wasn't able to represent illegal state, and now you can, if the main message acts as a generic argument, you can have a reply message with an egg, which is I think kind of invalid.
Sorry, what do you say that it introduces illegal state, or?
Yeah, because as I understand, the main message acts as a generic argument, as a generic parameter of message invalid. So now you have, you either have message of A, where A is either request or reply, or message with egg of A, where A either request or reply. So it's possible to have an illegal state when we are sending a reply with a knowledge.
That's actually a very good observation. And in our real domain messages, we don't mix request and reply in the same message, because usually it's not part of the same thing. Like messages a server receive, they don't contain a reply as part of the same discriminated union. So that in reality it can't happen.
Okay, thank you. It's not production code. I got it.
But with that, there is one important consideration about actors, that current state of .NET framework, and I think it also goes for Scala, that actor messages are by nature untyped. So even though we are very careful here, nothing prevents you from sending to your actor message 42. And that message will just go directly to dead letter box if your actor is unable to match it. There is an experimental project, it's on GitHub, it's called Ackling. The project is maintained by one of Akka contributors, and he actually, it's F# project, and he managed to create slightly different APIs that prevents you from sending any message to typed actor. So it has some guards, which I think has good potential. It's very promising. But currently, and this has to be exposed and tested, currently you can just send anything to your actor, and it will just route it to dead letter message if your actor is not capable of doing anything like that.
Okay, thank you. Thank you very much.
Thank you. Another question?
Oh, thank you for your speech. It was very good.
Thank you.
As far as I get you right, you are using the acknowledgement provided by MQP for transactional scenarios. And in case of some kind of exception, for example, during the business logic processing, some domain logic processing, would be good to know what kind of exception, what kind of things went wrong. Do you provide some mechanisms inside the system to propagate the exception to the caller or something like that?
So the question was, when something wrong happens and the message is not fully processed, it probably will be unacted. So how do we deal with this exception? How do we propagate it? One of the reasons we have chosen actor model is that act is created hierarchically, and then the creator of the actor always supervises it. And when exception happens, you can define supervision strategy for your supervisors, which means which basically consists of some pattern matching based on exceptions. So if exception happens, supervisor can decide one of 4 ways to deal with this message. It can resume it, which means that actor keeps its state and continues processing, which means that exception is not really important. It can restart the actor, and this is default. Then actor loses its state, but then it's up and running and can process more messages. It can stop the actor, which means, and if you're the only actor who, for example, talks to database, then you're screwed. Or it can escalate. It means that exception is so severe, for example, there is no connection to network. Then it will be propagated further up, and then the creator of that supervisor will manage with that. And this is one of the reasons for stability of actor-based systems, because while C#, Java, object-oriented languages, they also deal with exceptions, but they don't have built-in mechanism to restart pieces of codes. But I must say that now our code is, even though our code is in production, but it's still in development, and we're dealing now actually with problems of supervising, and sometimes it's very hard to decide what to do if some exception happens with a child actor. It's a bit new pattern for us. We haven't fully investigated it.
Okay, thank you.
Thank you. Okay, then there will be soon the very last talk, and we see the guitar here, so I guess it will must be interesting and creative talk. So let's take some break.
Аплодисменты Вагифу.
Thank you.